Hello everyone. In the previous lecture we had seen principal component analysis, shortly abbreviated as PCA. In this session um, we're gonna understand GMM model, that is Gaussian mixture model. But before diving into that lecture, we need to understand what is normal distribution, what is Gaussian distribution, and with respect to that, we also understand what is probability distributed function, PDF, and based on that we will understand GMM model, right? So let's say we are dealing with normal distribution. So let's say this is the graph for x, and the middle component is to be known as mu, and mu represent here mean, or you can say mode, or whatever the average you want to take. This is the mean, and this distance between the mean and this curve is known as variance, and variance can be represented as sigma. Okay, so this is sigma and this is mu, and this is the graph for x. Now the thing is, what we can say from this graph is that this x is going to be distributed Gaussian, in a Gaussian way, in the graph. Okay, the value of x is being distributed. It is a Gaussian distribution. Whatever the feature space of this x is having, they all are Gaussian distributed. Okay, they all are Gaussian distributed. So I can mathematically represent this. I can say that my x belongs to some dimension. Okay, some dimension, and it is so this is the first point. This is the it is I can say x belongs to some dimension, and x is heavily Gaussian distributed, and I can mathematically represent that thing with the help of, this is my x, this is the normal distribution. uh, Actually this symbol represented as distributed as. Okay, this symbol is represented as distributed as, and I can say that this x is normally distributed by taking two parameters. One parameter is your mean, and the other parameter that I'm going to take is your sigma square, or you can say just write sigma. So this is your mean, this is going to be variance, and possibly this n represent here as normal. So I can say from this graph that my x, this x is belongs to some dimension, and it is Gaussianly distributed, and I can mathematically draw it out from this equation that x is distributed as normally by means of taking mean and by means of taking this variance. Okay, so now what other conclusion you can draw it out? The other conclusion, just let me scroll it down here. Other conclusion that you can draw it out from here is, let me just change the color, and I can say here that this if x is in middle, that means x is high. It's pretty easy to understand, right? If x is in the middle, then x is very high. As Gaussian distribution, this GD is Gaussian distribution, your Gaussian distribution is high. Okay, this is self-explanatory, I think. And if you go for, like, if x is taking place, if x is taking place to more of left or right, then you can say if your x is going to move from this central location, right now this x is here, actually I can say this x is here, and if it is in the middle, then you can say that the mean is very high, and the point where x is right now belonging is very high. That means Gaussian distribution is high right now, right? You can tell that. However, when your x is going to move from right or I mean left or right, then your Gaussian distribution is, basically you can say this is the lower part of Gaussian distribution. So your, if x taking place to move from off left or right, then it means that your Gaussian distribution is low, okay, or you can write it as x is low. Okay, this is the thing you can tell from the graph. If x is in the middle, then the Gaussian distribution is high. If x is taking place to move from left to right, then there might be the lower performance of Gaussian distribution, right? Now this graph that you had drawn it out here, I again draw it. So I'll put it. This is the x, this is mu, and this distance is going to be my sigma square or sigma. And this particular thing, this graph, is basically known as PDF. Okay, this is PDF, and I will write it down: probability density function. This is PDF of x basically. So if you are having larger number of x, x1, x2, x3, then then x1 belonging to PDF1, or you can say PDF1 belongs to x1, then PDF2 belongs to x2, likewise. Okay, there are so many PDFs is going to be generated according to your x variable. Okay, so this graph, this complete graph is the PDF graph, or you can say the PDF wave of x, and I can mathematically show it, that p, that means the probability of x, can be given by mu and sigma square. More precisely, you can write this equation in a more mathematically: 1 by 2 pi under root sigma exponential minus x minus mu, which is the feature scaling, to square, and again this is in the whole square. Okay, so this probability density function can also be put it down here in this way. Okay, so this is PDF, this is PDF in more generalized way, and this is the PDF of x. So what do you mean by probability density function? I will write it down here: PDF. Well, PDF is a mathematical function. So this is a mathematical function that provides the probability, it provides you the probability of occurrences of different possible outcomes in an experiment. So I hope you are getting it. So PDF is nothing but a mathematical function that gives you a kind of probability of a certain variable, or whatever the input you are giving. So if there is x, then PDF is going to find the probability of x, where it is residing, and what kind of possible outcome the x going to give you according to the experiment. So my experiment is like, let's say the x is the random variable here. Let me say this is a random variable, and my experiment is to coin a toss, coin for toss. Let's say this is my experiment, and I want that what kind of outcome it can give you, what kind of possible outcome it can give you. Then you can simply say that this random variable is going to give you the PDF. Okay, PDF of x is going to give you the possible outcome is going to be head. The probability is going to be 50%, and the possible outcome is it can be also tail, possible and the probability of tail having 50%. Okay, so these are the probability, and these two, head and tail, are nothing but possible outcome of by coining a toss. What is this? This is possible outcome. Okay, I hope you are getting it. So if x is your random variable and the experiment is to coin a toss, then the PDF of x is going to be head and tail, because that is the only possible outcome when you are tossing a coin, right? And the probability that head comes is going to be 50% and tail is going to be 50%. So this is the PDF, and the graph that it looks like is going to be like this only. Okay, so 50%, if your x is to be here or here, then the GD is going to be lower down, and if your x is at the middle point, then your GD is going to be very high. So this is the probability density function. More precisely, this is Gaussian distribution. Okay, and and you can also see over here that the graph is having certain variation. So the first variation, if my mu is going to be 0 and my sigma is going to be like 1, then you will get, so this is 0, this is 1, this is 2, likewise this is -1, this is -2. Then if my mu is on the 0, then this is the graph I'll get, and this is my sigma. Okay, and this is basically mu. In the same way, if my mu is going to be like 0 and my sigma is going to be like 0.5, then the same graph is going to change a little. So this is going to be like this. I cannot draw it properly, but this is actually here. This is going to be 1. So this is going to be 0.5, and this will become your sigma, and this will become your mu. In the same way, if your mu is equals to let me just mu is equals to like 3 and sigma is equals to 0.5, then you just have to shift your mu to a little 0, 1, 2 and 3. This is where this graph is going to give. This is 3, and this is going to be your mu, and this is going to be 0.5, or say this is sigma. Okay, so this is how your mu and variance is going to be variated according to the parameters you give to the mean and variance. Okay, I hope you understand what you mean by Gaussian distribution, and according to the Gaussian distribution, we're going to understand the Gaussian mixture model. Okay, so let's flip the topic now and understand what do you mean by Gaussian mixture model. Okay, so this is a topic for unsupervised learning, and GMM, basically what this GMM does, now keep that in mind, that you're dealing with unsupervised learning over here, right? And what is the outcome of unsupervised learning? Nothing but a kind of pattern, and by means of saying pattern, speaking to which, actually we are dealing with clustering here, right? So if I'm saying set of patterns, then it is nothing but clustering, right? So here the Gaussian mixture model will give you a kind of clusters, right? This is exactly what we want in unsupervised learning. So what will happen in Gaussian mixture model? I'm again going to draw one graph here. So this is the graph, and I will not having the only one PDF now. I do have different PDF. Okay, so these all are the PDF of different x's. And why do I have it? Well, basically you understand that in the data set we don't have only single component as x. This is the you can say the regression for one variable. However, in the data set, in the unsupervised learning data set, we have different component of x1, x2, x3 and so on till maybe xm, right? We have so many columns there. So every column is going to give you PDF, right? It will give you a PDF1, PDF2 and PDF3. So this is the PDF of one random variable. Okay, PDF of one random variable, let's say x1. Then this is going to be PDF of another random variable x2 and so on. So it could be like for x3, and it could be for x4. So what we understand is that as this is a mixture of data, so we have multiple PDF for random variable from dataset, right? If I have 4 points x1, x2, x3 and x4, then I'm going to get 4 PDF for PDF1, PDF2, PDF3 and PDF4, right? And also there is one more thing that we need to understand. So I'll write it down here. Where I'll write it down over here. So a of PDF of mixture of distribution, PDF of mixture of distribution is a linear combination. It is a linear combination of these individual PDF. What do you understand? What can you understand from this statement? Well, what it says that, let me just understand that if I am having individual PDF, then there must be one single PDF that can be drawn for these x1, x2, x3 and x4. What I mean to say is, let me just take another color here, and so the graph is this is one PDF, another PDF and another PDF. So what I can say here, these are the individual PDF, but however these individual PDF is also having some linear combination. So linear combination going to be look like this. Okay, this is not exactly the PDF that I want, but this is the PDF of mixture of distribution. I hope you are getting it, that this is the PDF of mixture of distribution. However, these PDF or maybe these PDF are the individual PDF. Okay, so these are the individual PDF. However, this line is basically the PDF mixture of all individual PDFs. This is the linear combination. I hope you are getting it. Okay, so this is in 1D, by the way, this is in 1D. When I represent this in 2 dimension, this linear combination, in 2 dimension, this linear combination is going to look like this. So actually I need to draw it like here. In 2 dimension, it is going to be look like this. So these are the variables of x. These are the data set actually, x1, x2, x3, x4 and so on. So in 2 dimension, what I'm gonna do is these are the individual PDF or individual x1, x2, x3 and x4. However, for the linear combination, what I'm gonna do is, for linear combination, it is going to be like this. Okay, and then so this is the PDF of mixture of distribution. Okay, so this is the PDF of mixture of distribution, and these are basically the counter lines, and you can say this is counter lines, and these are the individual PDF. So sorry for all this spelling mistakes. So you can understand, in 1 dimension this is the linear combination, this line. However, in the 2 dimension, this is the line that represents the linear combination or the PDF mixture of all PDF. Okay, so in 2 dimension, and that in the 1 dimension, and you can observe that we can see that these are the clusters actually. This in 2 dimension, you are getting some clusters. You can see here in this diagram. Can you see this is cluster 1? It can be cluster 1 and it can be cluster 2. And mathematically I can redrawn it out. So what I can say here, that let me take mathematically, so I'm taking z variable here, and z variable is my latent variable. Okay, it is a random variable. This is my latent variable and also the random variable. Now, what do you mean by latent variable? Now latent variable it means that I already have x. Okay, it actually this z represent here, it represents my x variable, right? I cannot use this x variable to mathematically drawn out some observation. I cannot use this x variable directly, so I need some another variable. By means of that I can draw out some observation from the experimentation. Okay, I can draw. So I'm not using directly the x, but I'm using some other random variable. By means of that I can observe something, and those kind of variable are known as latent variable, where you cannot directly use the original variable, but instead of that you are using some dummy variable or random variable, and that variable is known as latent variable for modeling out the mathematics. Okay, so your z or z is a latent variable, and z here z belongs to some e of k, and e of k here is a feature set of e1 to, let's say, ek. Okay, so z belongs to some ek. It's a vector space, and here e1 can be like 1 0, or can be any um, some number. Okay, some number. So z belongs to ek, and this is given, so I can simply write it as like z is e of k, and you know that this x, z is nothing but your x actually. So I can also say that x here is distributed normally, but how normally? Going to be with mu of k and variance c of k. This is how I can say. Then I can say this is nothing but z itself. Then I can say that x is a Gaussian distribution here, or you can say z is a Gaussian distribution here, right? They are the same. So z or x is Gaussian distributed or normally distributed by taking mu k and ck. Here n is normal distribution, and let me just also draw it out here. So what I want to say is that mu1 to mu m, that is your mean, is basically belongs to d dimension space, and your ck is variance actually, but here variance, it means there is a covariance matrix. Okay, I'm using covariance matrix rather than to use variance. I'm using covariance matrix, and it also belongs to c1 to ck. Actually this is k, and it belongs to d cross d covariance matrix. Okay, d cross d matrix. And I can say that if my x belongs to some Gaussian distribution, then these e of k, these the feature space, the sample space here, these all are in the Gaussian distribution. Okay, if my x is in the normal distribution, then they are also in the normal distribution. I can simply say that, right? So what I can draw it out, that I can get if I'm only taking e1 and e2, then so if I'm taking z as e1 and e2, so this can give me two z1 and z2, and based on that you can draw it out here. So this is my z2 and this is my z1 cluster, and you can see these are the natural clusters that you can draw it out from the PDF of x, which are nothing but x1 and x2 itself, but we are representing latent variable, and that's why we had used z1 and z2. Okay, so it's nothing but you already know that in e1 we have 1 0 and so on numbers, and e2 is also having some numbers like 0 1 and so on. So we are representing that 1 0 and 0 1 here in this in clusters by taking some color. So those data points are going to be like it's going to be drawn like this. Okay, these are the data points 0 1 0 1 0 1, and you will get some natural clusters here, and so that's why I had said that Z1 and Z2 are natural clusters. Okay, and this can be drawn out from the Gaussian distribution model. I hope you are getting it. So earlier we have only one single PDF, and then we had taken out some like variables x1, x2, x3, and x4, and we get PDF1, PDF2, PDF3, and PDF4, and then we get some linear combination of that PDF, and we had seen in the 2D diagram, then we are getting some clusters, two clusters, and how we can model it with mathematics. We take a latent variable to represent x, and the latent variable here is z, and it belongs to a vector space ek, and from that we had taken only two, e1 and e2, which are having 1 0 0 and 0 1 0 0, and by putting those numbers inside this 2D, in this 2D graph, we can have this z1 and z2 cluster. I hope you are getting it. Okay, so this is your Gaussian mixture modeling. If you have any doubt, you can ask me in the comment section, and I'll be happy to resolve it. Thank you so much for listening to me.